Prepare to journey into the realm of the bizarre, where chemistry and curiosity meet to reveal materials that defy logic and stretch the boundaries of science. Here's the top 15 strangest substances ever discovered, starting with number 15, bacteria on Venus. The possibility of life on Venus is a subject of interest in astrobiology due to Venus's proximity and similarities to Earth. To date, no definitive evidence has been found of past or present life there. In the early 1960s, though, studies conducted via spacecraft demonstrated that the current Venusian environment is extreme compared to Earth's. Studies continue to question whether life could have existed on the planet's surface before a runaway greenhouse effect took hold, and whether a relict biosphere could persist in the modern Venusian atmosphere. However, research published in September of 2020 indicated the detection of phosphine in Venus's atmosphere that was not linked to any known abiotic method of production present Mars via methane was reported. And so on June 2, 2021, NASA announced 2 new related missions to Venus, Da Vinci and Veritas. Number 14, Galvorn. Galvorn has been described by materials development company Dexmat as a magic material that outperforms steel in strength and aluminum in lightness, while promising to drastically reduce carbon dioxide production. According to Dexmat, this revolutionary new material will make the use of copper in electrical applications such as car batteries obsolete and replace aluminum and steel in construction, automotive, and aviation industries. Galvorn is composed of carbon nanotubes, tiny cylinders of carbon molecules that are 100,000 times thinner than a human hair. These tubes have ideal physical properties for various applications. They're strong, flexible, lightweight, and excellent conductors of electricity. NTCs are used in electronics, energy, medicine, and construction because of these characteristics. Galvorn storage energy. Galvorn is produced industrially, and it's already commercialized in several formats, including a mesh that can be used to create composite panels, electrodes in clothing, a fiber for conductive cables, power lines, and motor windings. Its first commercial application, according to Dexmat, is in electrothermal wiring for de-icing aircraft wings. Number 13, biofilm. Biofilms are glue-like substances that encase clusters of microbes to provide extra protection against the elements. They can be found all throughout nature, even on the human body, where biofilms can lead to complications in wound care and adhere to your teeth as plaque. But they're also found on the ocean floor, protecting the microbial communities that set up shop near areas of methane accumulation. Where they're not usually found, though, is within the cracks and crevices of seabed sediment. That was until a group from the Center for Arctic Gas Hydrates, Environment, and Climate at the Arctic University of biofilm was highly unusual in this particular location, and could even play a role in terms of climate change. This was the first case of biofilms visible to the naked eye found in the cracks of methane-rich sediment, and they could prove to be a common occurrence of which we're previously unaware. Number 12, a speleothem. A speleothem is a geological formation of mineral deposits that accumulate over time in natural caves. Now, speleothems most commonly form in calcareous caves due to carbonate dissolution reactions. They can take a variety of forms depending on their environment. Their chemical composition, gradual growth, and preservation in caves makes them useful paleoclimatic proxies. In caves, the 6 most common types of speleothems are flowstone, columns, drapery, stalagmites, stalactites, and straws. Many factors impact the shape and color of speleothems, including the chemical composition of the rock and water seepage rate, water flow direction, variations in precipitation after the width of speleothem rings. Closed rings indicate little rainfall, wider spacing indicates heavier rainfall, and denser rings indicate higher moisture. The drip rate counting and trace element analysis of the water drops record short-term climate variations, such as El Niño, the southern oscillation of climate events. Exceptionally, though, climate proxy data from the early Permian period have been retrieved from speleothems dated to 289 million years ago, sourced from infilled caves exposing by quarrying at Richard Spur locality in Oklahoma. That is just a whole lot of words put together. Number 11, Lake of Liquid Sky. Every now and then, mankind discovers incredible things that truly amaze us. And this network of virgin cave passages uncovered beneath Carlsbad Caverns National Park in New Mexico definitely fits the bill. At around 700 feet below the park, a pristine pool never before seen by human eyes was revealed. The park posted on their official Facebook Sky, and this latest discovery could yield more amazing results. Lechuguilla Cave was known until 1986 as a small, insignificant historic site in the park's backcountry. Small amounts of backguano were mined from the entrance passages for a year under a mining claim filed in 1914, and the historic cave contained a 90-foot entrance pit known as Misery Hole, which led to 400 feet of dry, dead-end passages. However, in the 1950s, cavers heard the wind roaring up from the rubble-choked cave floor. Although no route was obvious, people concluded that cave passages lay below the rubble. Led by Dave Allered, a group of cavers from the Colorado Grotto gained permission from the National Park Service and began digging in 1984. Explorers have mapped over 138 miles of passages, making Lechuguilla the 8th longest cave in the world and 4th longest in the U.S. Drawn by the cave's pristine condition and rare beauty, cavers come from around the world to explore and map its passages and geology. Really anything and watch the show. All that's required for it to blow up is simple contact or friction. This material is so unusual due to its volatility that even touching it can cause it to explode. Other chemical compounds with triiodide in their name may contain 3 iodide centers that are not bonded to each other as the triiodide ion, but exist instead as a separate iodine atom or iodide ion. In solution, it appears yellow in low concentrations and brown at higher concentrations. The triiodide ion is responsible for the well-known blue-black color, which arises when iodine solutions interact with starch. Iodide does not react with starch, nor do solutions of iodine in nonpolar solvents. The redox reactions of triiodide and iodide have been proposed as critical steps in dye-sensitized solar cells and rechargeable batteries. Number 9. Vanta Black. Vanta Black is an artificial material that was developed by Surrey Nanosystems. This coating goes on many things, from paint. The goal was to create an experience of being absorbed into blackness, a deep, dark cloud of black. Early development occurred at the National Physical Laboratory in the UK, and the term Vanta being coined later in its development. Controversy arose, though, when Surrey Nanosystems granted Anish Kapoor exclusive rights to use Vanta Black in artistic applications, with many artists voicing opposition to his monopoly over the substance. In response, Nanolab, a Waltham, Massachusetts-based carbon nanotube manufacturer, partnered with a Boston artist, Jason Chase, to release a nanotube-based black paint called Singularity Black. During the first showing of the color, Chase, alluding to Vanta Black, stated that, quote, "Its possibilities have been stunted by not being available to experiment with," end quote. And Singularity Black's release was an important thing to create access. Number 8. Ultra-hydrophobic material. Ultra-hydrophobic material isn't the stuff we buy to coat leather and suede products or fully rebound like an elastic ball. The fine hairs on some plants are hydrophobic, designed to exploit the solvent properties of water to attract and remove sunlight blocking dirt from their photosynthetic surfaces. Water striders are insects that live on the surface film of water, and their bodies are effectively unwettable due to specialized hair piles called hydrofuge. Similar hydrofuge surfaces are known in other insects, including aquatic insects that spend most of their lives submerged, with hydrophobic hairs preventing entry of water into their respiratory system. The skin surface of some species of lizards, such as geckos, has also been documented as highly hydrophobic and may facilitate self-cleaning or underwater breathing. Moving on to number 7, ferrofluid. Ferrofluids, they're a type of liquid that can easily be formed into strange shapes without even touching them. Often dark, blackish, reddish, or grayish liquids, ferrofluids act very much like any other liquid when they're inhibiting clumping. These large ferromagnetic particles can be ripped out of the homogeneous colloidal mixture, forming a separate clump of magnetic dust when exposed to strong magnetic fields. Ferrofluids, however, usually don't retain magnetization in the absence of an externally applied field. A process for making ferrofluid was invented in 1963 by NASA's Steve Papel to create a liquid rocket fuel that could be drawn towards a fuel pump in a weightless environment by applying a magnetic field. But they've got many other uses as well. Ferrofluids are used to form liquid seals around the spinning drive shafts and hard disks, and the rotating shaft is surrounded by magnets. Ferrofluids can also be used in semi-active dampers in mechanical and aerospace applications, while passive dampers are generally bulkier and designed for particular vibration sources in mind. Active dampers consume more power. Starting in 1973, ferrofluids have been used in loudspeakers to remove heat from the voice coil and to passively damp the movement of material created under certain circumstances of temperature and pressure. It suspends the dividing lines of physical properties as we know them. In short, a supercritical fluid is a substance somewhere between a liquid and a gas. It's a mixture of both, and yet neither is a liquid nor a gas. It occurs when any fluid gets heated above its critical temperature and pressure. Critical temperature is the point where a substance has been heated to such a degree that you cannot liquefy it, whereas a critical pressure is the pressure that's needed to turn a gas into a liquid at a high temperature. If you were to delve into the atmospheres of some planets like Jupiter or Neptune, you would be immersed in it. So yeah, supercritical fluids happen in the atmospheres of the gas giants Jupiter and Saturn, the terrestrial planet Venus, and probably in those ice giants Uranus and Neptune. But supercritical water is also found on Earth too, such as the water issuing from black smokers, a type of hydrothermal vent. Carbon dioxide and water are the most commonly used supercritical fluids. Nitinol is often used in the medical industry, but it has other applications. The weird thing about this metal is that it's almost like the liquid metal featured in the movie Terminator 2: Judgment Day, in that it can always return to its original shape. In other words, nitinol has superelasticity, or memory, for its original form. So if you make an object out of nitinol and then bend it completely out of shape, it'll automatically crawl back to its original shape before your eyes. These memory properties make it both fun and practical. Stents, for instance, are a great application, as nitinol can bend within the human body when needed, and has the durability of a metal, and then can return to its original form every single time after the force which causes it to warp is released. Nitinol's bending, shape-shifting properties are usually activated by heat. At some temperatures it will bend out of its original state, at others it will return to its original state. This temperature difference can be controlled within 1 degree Celsius. The word nitinol is exceedingly difficult to make due to the exceptionally tight compositional control required. Vacuum arc remelting is done by striking an electrical arc between the raw material and a water-cooled copper strike plate, and melting is done in a high vacuum, and the mound itself is water-cooled copper. Vacuum induction melting is done by using an alternate magnet field to heat the raw materials in a crucible, generally carbon, and this is also done in a high vacuum. Number 4. Gallium. Gallium is a metallic element with the atomic number of 31, which even more closely resembles the liquid metal from Terminator 2. Gallium's particularly strange characteristic is the low temperature at which it liquefies, which is only a tad shy of 30 degrees Celsius. That's close to room temperature in many places. This metallic element is bright, shiny, and a silvery white in color. When you handle gallium, there's no ambiguity that you're handling a liquid metal. As a liquid, the metal can be played with. It rolls and forms into various shapes. Gallium liquid expands by about 3% when it solidifies. Therefore, it shouldn't be stored in glass or metal containers, because the container may rupture when the gallium changes state. Gallium shares the higher density liquid state with a short list of other materials that includes water, silicon, germanium, bismuth, and plutonium. Gallium forms alloys with most metals. It readily diffuses into cracks or grain boundaries of some metals, such as aluminum or aluminum-zinc alloys and steel. And it's also one of the 4 non-radioactive metals, with cesium, rubidium, and mercury, that are known to be liquid at or near normal room temperature. Of the 4, gallium is the only one that is neither highly reactive, as are rubidium and cesium, nor highly toxic, as is mercury, and can therefore be used in metal and glass high-temperature thermometers. Number 3. Hydrogel. Hydrogels are a fascinating group of substances, not unlike supercritical fluids. However, instead of being suspended somewhere between a liquid and a solidify and still be flexible is mind-blowing. The term hydrogel was coined in 1894, and since then they've been investigated for diverse applications. The variability of mechanical stiffness is why hydrogels are so appealing for biomedical applications. Characterizing the mechanical properties of hydrogels, however, can be pretty difficult, especially due to the differences in mechanical behavior that hydrogels have in comparison to other materials. In addition to its rubber elasticity and viscoelasticity, hydrogels have an additional time-dependent deformation mechanism, which is dependent on fluid flow, called poroelasticity. These properties are extremely important to consider while performing mechanical experiments. Some common mechanical testing experiments for hydrogels are tension, compression, confined or unconfined, indentation, shear rheometry, or dynamic mechanical analysis. Number 2. Graphene aerogel. Graphene aerogel is the lightest material on Earth and definitely the lightest solid material of all known solid materials. On top of being used for many adhesives, coatings, and fillers, graphene aerogel is also being developed as a lightweight material for 3D printing that produces precise results. Despite the name, aerogels are solid, rigid, and dry materials that don't resemble a gel in their physical properties. The name comes from the fact that they're made from gels. Pressing softly on an aerogel typically doesn't leave a minor mark, although pressing more firmly will leave a permanent depression. Despite the fact that it's prone to shattering, it's very strong structurally. Its impressive load-bearing abilities are due to the dendritic microstructure, which spherical particles are fused together into clusters. These clusters form a three-dimensional, highly porous structure of almost all fractal chains, with the average size and density of these pores being controlled during the manufacturing process. Number